Welcome back. In this video, we're going to talk about critical points, Fermat's theorem, and the second derivatives test. Definition 4.1.3. A point AB is called a critical point of a function f of xy if AB is in the domain of f, and either the gradient of f at AB is 0, or the gradient of f at AB does not exist. Note that if the gradient is the 0 vector, that means that both of the partials, f sub x at AB is 0 and f sub y, both of them must be 0. Whereas if the gradient does not exist, that means at least one of, not necessarily both, at least one of f sub x at AB does not exist, or f sub y of AB does not exist. Example 4.1.1. Find the critical points of f of xy is x squared plus 2x plus y squared minus 4y plus 8. We need to investigate two types of places. We need to investigate where the gradient of f equals 0 and where the gradient does not exist. We'll do that one in just a second. So the gradient equals 0 when f sub x equals 0 and f sub y equals 0. So let's calculate the two partials. F sub x is 2x plus 2. F sub y is 2y minus 4. If we let each of these equal 0, if 2x plus 2 is equal to 0, we have that x has to be minus 1, and 2y minus 4 equals 0 gives us that y is equal to 2. So we have minus 1, 2 as a critical point. Places where the gradient does not exist, well, this is a polynomial, there are none. Therefore, the point 1 minus 2 is the only critical point. Theorem 4.1.1. Fermat's theorem for functions of two variables. Let f of xy be continuous on an open set containing AB. If f has a local extremum at AB, then AB is a critical point of f. Students very often confuse Fermat's theorem to mean that local extrema and critical points are one and the same. They're not. A paraphrase of Fermat's theorem is that critical points give us a list of candidates. Candidates only for local extrema. To investigate each candidate, whether it actually is a local extremum or not, we need the following. Theorem 4.1.2, the second derivatives test. Notice there is an S, because we are in functions of two variables, we have multiple second partial derivatives. Suppose the second partial derivatives of f are continuous on a disk with center AB, and suppose that the gradient of f at AB is 0. Let d of AB be the following. F sub xx of AB times f sub yy of AB minus f sub xy of AB squared. If d is greater than 0 and f sub xx of AB is greater than 0, then f of AB is a local minimum. If d is greater than 0 and f sub xx at AB is less than 0, then f of AB is a local maximum. And if d is less than 0, then AB is a saddle point. A couple of notes to read. One that I'd like to say before we read the notes here is that these second derivative tests match Obviously, D doesn't match what you did in Calculus 1, but this idea of when the second derivative is positive, you have a function which is concave up, and therefore you have a minimum. And when the second derivative is negative, you have a function which is concave down, and therefore you have a maximum under the given conditions. Those line up with what you may be familiar with in Calculus 1. Note, if D is equal to 0, right, we have D greater than, D less than. If D is equal to 0, there is no information to be had, and the test fails. F could have a local extrema, a saddle point, you don't know. A little remark, H, which is the matrix of second partials, so f sub xx, f sub xy, f sub yx, and f sub y is called the Hessian matrix. What does that have to do with anything? Well, D just so happens to be the determinant of this matrix. So you remember from your linear course that the determinant of a 2 by 2 is AD minus BC. So if you take this product and subtract the other, if the partials are continuous, the second partials, those are equal, and you get exactly the expression for D. Since this matrix H is called the Hessian, D is often called the Hessian determinant. In the next video, we will do an example where we will find some critical points and classify them using the second derivatives test.